Thank you, Tim, and thank you, Sarah, as well. Let's see, is my audio pretty good, Sarah?
Yeah, you sound good, Dan.
All righty, thank you. So I've given this talk a number of titles. We'll get to Heraclitus in a moment, but a recent book just came out in Europe, and it's got several unconventional essays from the likes of Bill Dietrich and Sue Brantley, Jerome, and myself, and we were asked to write about the science and from a science of our observatory, and also what the science might mean in a broader context. And I'm a deep adherent to the observatory context, and so I felt like this was written in the midst of the NSF moving us a little bit more toward networking of observatories and much less about studying individual places and then networking those. So I put a lot into this little 4-page essay with Sharon, and I even open it here on a Sunday morning in April 2014. Historian of Geosciences, Dr. Enriqueta Barrera of the US NSF opened a meeting of several dozen Earth scientists, including a number of people who are listening today. Opened a meeting and those people were from across the United States. The group had gathered at Paget's Creek Baptist Church in rural South Carolina. This place is quite special, and I really appreciate how NSF in that 2013 panel had confidence in my team and myself and gave us this amazing opportunity that actually and frankly goes well beyond science. And if all I can say is look at this plantation house, which is in the middle, literally in the middle of the Calhoun experimental forest, and just look at this 1830s history in the midst of a cotton plantation that we've now done amazing history on, and we're working like heck to reinterpret it. More about that in a moment. But first, let's get to the title, advertised title, Heraclitus and Why You Can't Step into the Same Critical Zone Twice. Chances are you might have heard of one of Heraclitus's few dozen sentences. He writes in enigmatic fashion, and so he says, and this is one you've probably heard, you can't step into the same river twice. And I've always liked that. Many of us have always liked that, pondered it. And the traditional meaning is all is flux, all is change. And therefore, over the many hundreds of years, Heraclitus has developed this reputation of being the weeping philosopher, because nothing is permanent. There is no constancy. We're going to lose it all in the end. And that's his traditional interpretation. And what I'd like to do is use this title in context of Critical Zone to actually tell you about some contemporary rereading of Heraclitus, which really gives that statement a lot better of a twist and it's a lot more subtle, argues John Barnes, who's a longtime philosophy professor at Stanford. He asserts a different meaning as well as a careful retranslation. And he says, here's what it really says in authentic Greek: you cannot step twice into the same river, for fresh waters are flowing in upon you. And from that, Barnes asserts, as does many others, many contemporary philosophers, that flux and change are not destructive of constancy. Rather, flux is necessary to constancy. And so criticals are a thing, according to Dietrich, a thing because of their constant turnover of constituents. So what's wonderful about the structure of the critical zone are things like metabolism, the turnover of elements, the stresses, the strains, and most especially the evolution. Those are all necessary to the critical zone as an object of study, as a thing, and thus you can't step into the same critical zone twice. And the last thing I'll say about philosophy here is, if you haven't heard about it, the pre-Socratics, those people, a lot of them you've heard of, are having a resurgence. And here's right now, and in the last generation, and here's Heraclitus, but also Pythagoras, Epicurus, Euclid. You know, it's an amazing cast of characters of those who came before the famous ones, Plato and Aristotle and Socrates, but the pre-Socratics are really getting a lot of attention, and there are many others like Heraclitus, but he's definitely a leader in terms of what his influence even to today. So let's get a little bit closer to the Calhoun Critical Observatory and to natural science itself. And that is, let's look at the Calhoun landscape history, which I'm going to say reinforces Heraclitus's idea. And so the short thumbnail sketch of the Calhoun landscape is that although there were 10,000 years of inhabitation by the first peoples, 10,000 years, and there are many arrowheads scattered across this landscape from across those many cultures of 10,000 years. Those peoples left some mark on the land, and we have a couple papers on them and their influence, led by one of our colleagues who's an anthropologist. But really what happened was that in about 1780s, this upstate part of South Carolina was settled by Europeans and African Americans. And in terms of population, yes, the enslaved people were more or less than the Europeans, but they both together settled this land. And so what we're left with here is by 1920 or 1930, the economics of farming the Piedmont was almost impossible, and thousands and thousands of people left the southern Piedmont, and in any event, places like the Calhoun Experimental Forest were purchased by the federal government as a experimental forest to learn how to better manage the land. And so we have the 1933 U.S. Forest Service purchase aerial photos on the left, and you can read the landscape here by geo-rectifying it to, for example, one of our LiDAR flights from 2016 on the right. So I'd just like to go through these several sites here. Site A here is in a part of the landscape. Here's a scale down here, 1 square kilometer. These are small rounded hills that are just gullied, and perhaps 50 centimeters of soil has been lost from these uplands. That's hard land to walk across because of all of the incisions from the gullies. Up here in B is a location on the landscape, the legacy sediments, and if you think about all that lost, eroded soil, nearly all of it is still in the Piedmont, but it's down in the former floodplains in legacy sediments. And they probably, across our sites, those legacy sediments are 0.5 meter to 3, 4, 5 meters above the original surface. C, here's an interesting spot. It's out over here. It was only a few years out of cultivation in 1933, but here, after the photo was taken, the CCC had come in with their big 1930s bulldozers, smoothed this land, and built 2 meter tall dikes, basically terraces across the landscape. And then if you come further south, you can see D prime. You can see where those dikes and that land smoothing was basically blown out by some post-1930 storms that re-gullied that landscape. And last but not least is this place we call the Hardwood Triangle. You know, you can see that's almost a kilometer in length. This is a highly unusual landscape. You can see the convex hilltops and hill slopes and relatively smooth. And what we do is we have a paper on these Holocene or relic landscape surfaces, of which we estimate the Calhoun is occupied by about 0.1% or less of the Calhoun has these Holocene relic land surfaces still in existence. A prime is the typical situation across the Calhoun. In any event, yeah, 0.1% is occupied of the Calhoun Critical Zone Observatory has what we can consider a Holocene surface. If you go back to the 1933 Forest Service purchase photos and look very carefully, you can see the hardwood forest there, and you can also see some house sites. People were living in this hardwood triangle, but they were basically, this was owned by a small farmer who was basically a grazer. And he didn't cultivate, they didn't cultivate their land, but they rather basically lived in a hardwood wood lot, thus preserving the Holocene surface. I'm sorry this has gotten cut off, and on the bottom of this slide, I show you that we've got a paper by Billings, 2013, and another one, 19 Bonetti. Anyway, a lot of us have been interested in this part of the Calhoun. So let's move on. So the last of Heraclitus I'll deal with is dealing with what we're going to call the political landscape history of the Piedmont. I say this also reinforces Heraclitus. All this massive erosion, gullying, and sedimentation were initiated only by a century of Old South cotton. Only a century set all of this instability in motion with the labor of the enslaved African Americans and the very impoverished small farmers, white and black, that farmed the land from the Civil War through about 1920 or 30. One can't step into the same critical zone twice. Critical zone is all about evolution. It's nothing about restoration of the system. Okay, I'm going to take a break here and turn a little bit of a corner. Please email me, contact me if you have any follow-up questions. I've got a great team of you know, it's amazing. 100 scientists, students, 6 universities work at the critical zone. The U.S. Forest Service as well. We work with, we have a lot of participation. In any event, if you have any interest in coming to this place, we love to give field trips. One thing I've learned from being associated with all of you in the CZO projects is to start to think about the soil from the bottom up. I have learned so much from critical zone science, but this is one of the most exciting. Soil scientists typically think about the soil surface, you know, how we fertilize the surface, how we cultivate the surface. We tend to look pretty shallowly at the soil system, but what a marvelous thing to tell the story of the soil from the bottom up. And so that's another one of my titles in any event. We've recently put out a paper in 2020, Soil Production and the Soil Geomorphology Legacy of Grove Carl Gilbert. And here again, so much of this paper is rooted in stuff I learned and have studied with my colleagues in only the last 5 years. I compare this period of my scholarly life, this 4, 5, and 6 years, to be as exciting as my PhD years. That's how critical zone science can be. It's so incredible how much there is to learn and how much we have to share with each other our very special tools. And so here's a list of some of those people. But in any event, I have fallen in love with G.K. Gilbert as well, much less this idea and this science called soil geomorphology, which ebbs and flows. You know, some decades it's more vibrant than others, but here we're trying to rekindle that soil geomorphology, that pedology and geomorphology can be and should be folded together. So starting with a good friend of mine's photo, Jim Robertson, and here's a cross cut of a Palouse hilltop. And so it's very unlike the critical zone underneath the southern Piedmont, but it just tells us how diverse the Earth system is and its critical zones. And this is largely a wind blown and wind deposited critical zone, and layer by layer, they've accumulated, and you know, the thin layer of soil is right on top. In any event, the critical zone is a deeply extended ecosystem concept that actually is a quote more from Sharon Billings and I than Tom Jordan, but it's embedded in that 2000 report, and that 2000 report is a report not to just go on a bookshelf, but to keep it alive. So we tend to study soils from the top down. Let me get into this a little bit. It's really remarkably top down, and most superficially too. So here, Meg Mobley, a PhD student of mine who teaches at Oregon State, she made a histogram a couple of years ago of 360 studies of land use change effects on soil carbon. And 90% of these 300 studies on land use change on soil carbon sampled the soil 30 centimeters or less, as if there's no carbon below, as if the carbon below is stable or something. That's quite amazing. The median is about 15 centimeters. Incredible. And this is even though we know that there's lots of life and plants and animals that inhabit soil more deeply than most of our studies. And here's some 1920s evidence, a photo of an amazingly deep taproot of the wonderful species longleaf pine. And here's a corn. Here's an annual plant, which was mapped to extend its roots to 2.5 meters almost. They're to scale actually in terms of depth, the two photos. So we're well aware that there's a lot of carbon below the 30 centimeter mark. So it's very interesting to contemplate why our sciences have traditionally been so superficial in terms of thinking about, specifically, the soil system. So the critical zone science is just a great way for soil science to renew itself, to take advantage of the full range of processes below our feet. And so here's another title, and they're all related together, but this is going to be a much more continuous title through the remainder of the science of the talk. And that is that critical zones themselves and soils are clay factories. And I'm not the first one to mention this, but my colleagues and me are really pushing this hard. We argue with people like Bob Anderson in a very friendly way. He wishes factory were actually, we use the metaphor of a nursery, like, you know, the little baby nursery creates clay minerals. But in any event, critical zones and soils over the geologic time scale at which particle conveyors operate are nothing less than clay factories. And of course, clay minerals are some of the most important particles on Earth. And it's so incredible to think about and to study how they are actually synthesized and formed in this critical zone system. So again, we're going to tell the story of the soil from the bottom up. Yeah. Okay, so let's start with a little bit of 19th century wisdom. Always a good thing to do. Scientists in the 19th century were a lot less disciplined in terms of following disciplines and staying within their disciplines. And who know better than Gilbert, who, as he liked to say, he loved to engage in scientific trespass. Now, Gilbert's a lot more able than me at trespassing, but on the other hand, even for the likes of Gilbert, he was well aware that when you cross into another discipline, even if you know you have to, you're engaging in a trespass, of course, of sorts. So one of his favorite statements of many of us is one that says, over nearly the whole of the Earth's surface, there is a soil. And wherever soil exists, we know that conditions are more favorable to weathering than to transportation. Now let's say a couple things about this marvelous statement, that weathering outpaces on a net basis transportation. And he's speaking about the natural globe, not the Anthropocene globe, but the natural Earth system, that weathering outpaces transportation in a net manner. And he recognizes that what he calls soil, what we call regolith today, blankets the Earth. And it's so amazing. He's writing this from the Henry Mountains on a day off from his field work because it had snowed and rained, and he stayed in his canvas tent rather than, and sat down in his chair and started to reflect a little bit. And apparently in the Stanford Geology Library are his journals that actually relate that day and that day of work that GK engaged in. But just to think of it, he was appreciating the face of the Earth, the whole of the Earth's surface. And just think of the diversity of climate, geology, and all the rest, the diversity from the tundra to the tropics, from the deserts to the rainforests. We have soils blanketing the Earth. And according to his realization there, the great forces of weathering on a net basis were exceeding transport nearly everywhere. What an amazing statement. He was not the only 19th century genius to realize this. And I love it that not in geology, but in biology, although one must say that biologists have captured Darwin from the geologists. Darwin holds several of the greatest geological awards awarded to anyone on Earth. But the biologists have captured Darwin. But look at this. In Darwin's last book on the lowly earthworm and how the earthworms engage in bioturbation, and how fast do earthworms turn over the soil? Darwin is a real progenitor of so many sciences, including soil science. But read this. He says in 1882, his last book on earthworms, although the superficial layer of soil is no doubt of the highest antiquity, yet with regards to its permanence, superficial particles are removed at not a small rate and replaced by others due to disintegration of underlying materials. And here we have the particle conveyor. Oh my gosh. So here's soil, Gilbert soil, or what we call today regolith, the entire weathering profile. And W exceeds T on a grand net basis over geological time. And here at the Calhoun, this profile is deep. And so you put these losses and gains together, it's quite interesting. The landscape is lowering as a result of weathering, moving into the bedrock, liberating particles, and losses, transport. Here's the transport losses, both erosional on the surface, that would include soil creep and overland flow, but also the dissolution and drainage loss of the weathering reactions. But in any event, weathering exceeds transport at the Calhoun quite considerably because thanks to Steve Holbrook and Sue Brantley and Virginia Marcone and many other people, in a 2019 paper, we argued and we settled on 38 meters. 38 meters was the first evidence of weathering in our humble opinion. So here we have this regolith, this Gilbert soil that is extremely deep and extremely old as well, as I will get into in a moment. So then we can think about how this soil geomorphological system works. And I said it before, I've been totally in awe and benefited from the likes of Bob and Suzanne Anderson. This book they've written in 2010 is a classic. And then all of the students that Dietrich has moved through Berkeley is just amazing to work on this hill slope problem that is basically a Gilbert problem because of Gilbert's 1909 paper on the convexity of hills. So, but in any event, since the 1980s, since the 1990s, geomorphologists have, without a lot of pedologists, without the soil science community largely, there are a few exceptions, but they've estimated the rate of the soil conveyor, what they call soil production, or what Bob calls mobile regolith production, and the rates might range across these huge orders of magnitude here, less than 1 to 500 meters per million years. Perhaps Bill could help me with that range a little bit, but in any event, we're using cosmogenic radionuclides. We rely on steady state assumptions and constant depth assumptions and constant velocity of soil creep. But we can make these estimates that we're totally unable to make before. We can quantify what Gilbert only dreamed about in his just amazing descriptions of this critical zone system. Just amazing. And so let's do a little introductory to the southern Piedmont of North America. I've got it illustrated in the map up on top. Actually, the Piedmont rocks are under Manhattan. But across central Jersey, southeast Pennsylvania, Maryland, Virginia, and this is the majority of the land surfaces in the south, thus the southern Piedmont. Half of it's granitic or granitic gneiss derived. It's still conceived to be largely weathering in place. 90% of the soils are mapped as residual soils, weathering in place. It's, I say down here, it's the boring, gently rolling southern Piedmont. But to Calzones, we think of it as one of the most exciting places on earth. And I don't mean that just facetiously. I am absolutely earnest in saying that, because under these gently rolling, boring hills are so many tales yet to be told, so much to learn. This whole business up here on the upper left, that 90% of this whole region is weathering in place, soils weathered in place, derived from the bedrock directly below, is one of the last things that the Calhoun Critical Zone Observatory is banging away at right now, hot and heavy. And I'll touch on that at the very end of this talk. Very exciting. However, to be in a position of laying claim in a humble way that the conventional stories of a whole region have yet to be fully told, and I'll leave that for the very end of our talk. So, drill the ridge. So many of us remember that slogan a couple years ago. I remember when Sue and Bill gave talks, and at a particular meeting that we have, Drill the Ridge. Well, Alan Bacon and I had a little seed grant in 2009, 2010, and we took our, whatever it was, $15,000 or something, and we drilled the deepest hole we could go. And we were actually out on the drill rig making calculations. Oh, we can go 5 more meters. We can go 3 more meters. You know, we just had this in place. So what we did was we located what in 2010 we thought was very low curvature, very low geologic erosion, part of the surface. We went to the upper interfluve, and here you can see the LiDAR cross sections on the right. But in any event, the top of the landscape at the Calhoun are these broad, kilometer wide interfluves. And then the river systems here, the Tiger to the north and the Enoree to the south, are draining to the southeast. But in any event, a fascinating place. So we went to what we considered was one of the most geomorphically stable parts of this landscape and drilled a well that was, it was 70 meters. It's collapsed a little bit in the bottom to 65. So you see a couple of references to 70 and 65. But in any event, this is kind of interesting what we've done. We put the 38-meter mark here on these core boreholes, Steve, so you can kind of see where that 38-meter mark, which is the initiation of weathering, where it exists in proximity to the deeply incised gullies in the nearby hill slopes. So yeah, every one of these little stream valleys is incised and deeply gullied because of the agricultural history of the landscape. And it's again, that was only it was on the order of a century of agriculture, a lot of cotton, but a lot of crops and a lot of cattle and pigs. And by the end of the 19th century, a lot of the density of people out here was amazing. So a lot of intensive land disturbing activities for on the order of a century. And then we've had a century of reforestation. So that's the story here. Okay, and I reference Alan Bacon's geology paper in 2012, which he used he used meteoric beryllium-10 to date the weathering profile, and we came up with a minimum estimate with that less constrained of beryllium-10 methods of at least 2 to 3 million years for this particular weathering system to have operated like it's doing today, or in some semblance with how it's operating today, because we don't want to forget Heraclitus, a 2 to 3 million year system at most has experienced enormous climatic changes, enormous vegetation differences through time. So these weathering gains and these drainage losses and erosional losses have ebbed and flowed quite considerably. So let's look at this same system and get to it. So Bacon came out in 2012. We drilled the hole. I've already mentioned this. We say we quadrupled the age of the Piedmont. Holbrook in 2019. This is a nice team effort. It included geophysicists and geochemists. Concluded that the deep physical chemical weathering boundary was at about 38 meters. Lots of rock fracturing above that for about 20 meters. And then the saprolite and the soil were 20 meters perched on top. I've got a paper out, I just mentioned 2020, and then another one, the clay factory paper, hopefully submitted within months. Bob Anderson has taken our cosmogenic data and estimates a conveyor rate here of about 7 meters per million years. Very interesting rate. And then we're studying the generation of clay minerals as weathering products in much of the rest of the talk today. Okay, so the first thing you got to do is characterize the parent in any of these studies. And boy, there were a lot of conversations in the Holbrook-led effort about the nature of the parent. And so what Alan and I just decided to do, we got one core hole. We hit the base of weathering at 38 meters. And what we're doing here is we were compositing 3 meter deep cores into the bedrock. And so this is a lot of data, but you can see the means and the CVs down below. You know, the potassium's from the micaceous fraction of those minerals, 2.5%. I mean, that's pretty damn good. It's largely a siliceous granitic gneiss, of course, 70%. Pretty tight control there. Zirconium's a little looser there, 13.5% CV. Iron's up there at 16 or so. Calcium's a lot more variable than sodium, as the two cations of the plagioclase there. But in any event, this is very important. I don't think we do this enough, you know, and we all know that the parent rock is variable, and we ought to spend as good an effort as possible characterizing the parent. In any event, a lot depends on it. Okay, so that's a little bit there. So we gave that totals data to Virginia Marcone, and she produced a geochemical model of the constituents. And here is our first part of the two parts of the rest of the story here. Critical zone is a clay mineral factory. And this is textbook stuff in a lot of ways, except we've got the 7 meters per million years. That's pretty nice rate at which things are proceeding. This also strikes me like Heraclitus as nothing but a river. Think about this, a river that ebbs and flows through time. So here's 38 meters. Weathering, the ultimate zone of weathering is at 38 meters for physical and or chemical together processes, soon together, if not one or the other. But in any event, we get fracturing of the underlying bedrock because of the regional and the local stresses that I've learned are enormous. Preconditioning the bedrock for critical zone development. And just look at the first of the two feldspars here. So here's plagioclase on the order of almost 40% of the parent rock, moving up here to about 12 meters where it's all dissolved. It's all dissolved by 12 meters. I mean, the weathering front for plagioclase is deep by lots of measures, 12 meters. Orthoclase persists quite a bit more, but however, by 2 meters, 1.5 meters, it also is gone. In any event, the product is largely kaolinite, and here are the two big feldspars. And we know in our textbook, chemical and geochemical books, these two feldspars, you know, dissolve. A lot of calcium, a lot of sodium, and eventually potassium leached away, largely with bicarbonate. So soil respiration, the potent acid of CO2 and carbonic acid is an important part of the weathering agent, weathering agents, including the oxidation, reduction reactions, oxidation reactions of biotite, for example, but also the geophysical stresses. So in any event, here's critical zone as a clay factory. And it is a bit textbook, but it is important to think about. This is the origination of all the clay that's out, or much of the clay that's out there in the more sedimentary soils and landscapes of the world. This clay is, in this case, kaolinite, but there's a wide variety of clays. And we can read a book that a colleague of mine, Paul Schroeder, recently published, Clays in the Critical Zone. And if you haven't seen the book, everybody here needs a copy. Clays in the Critical Zone. It's a Cambridge book, and I think it's a 2018 publication date. In any event, here we can. I've ad-libbed this stuff on the right, so I'm going to move ahead. But weathering liberates the particles, no matter if it's quartz or the feldspars. They ride a particle conveyor to the surface, all while being attacked by soil respiration CO2, carbonic acid, all while enduring the redox potential shifts that go on on this strange sort of conveyor to the surface of the land. Between 38 and 10 meters, carbonic acid solubilizes plagioclase. I continue to be totally amazed at this, that the plage is almost all gone by 12 meters. well below the depth of roots. The products are kaolinite and some other clays. And now to tip my hat to Paul Schroeder, who is a biotite, illite, muscovite expert. Our paper, The Clay Factory, will fully embrace that very important stream. If these feldspars are rivers, in the background, you got a very important stream of the 2-to-1 clays of illite and muscovite, et cetera, that persist like orthoclays well into the soil on top. Very important stream. I'll let Paul and our paper take that up, and I'll stick with the big rivers here, the rivers of feldspar that are leaving behind kaolinite. In any event, okay, let's move ahead. Here's just a little tip. Calhoun's porosity, you know, the critical zone porosity is also a weathering product. And thanks to Brad Carr and others of Holbrook's colleagues, we got a picture of porosity. And you can see that it's entirely within what we're calling the saprolite. That porosity goes from 10% or less to a soil-like value or a sapro-like value of 50%. Beautiful weathering product data set there. In any event, that's opening up the critical zone to water, gases, solutes, life, and it's a product of both the physics and the biology and the chemistry. Just a great paper, Steve, and way to go in leading us here. I've synthesized a lot of our properties here. We can go kind of quickly. Look at this plagioclase. Okay, even at 18 meters, it's less than the original parent. Here's orthoclase that dissolves more toward the end of the conveyor. And of course, tau potassium and tau calcium and sodium are part of that story. The amazing thing here is that feldspars, as they dissolve, I mean, that's a pretty robust substitution there. Pretty interesting. Here's the formation of porosity on the bottom left, thanks to NMR. Amazing. Here is, I think this is Dan Markowitz's pH of salt, or maybe Alan Bacon's. Look at these acidities, man. It's pH 4, and even at 12, it's less than 4.5 in dilute calcium chloride. These granitic gneisses have weathered to an extreme stage of weathering through many meters of saprolite and soil. Here's the base saturation pattern. Correlated with the pH, of course, and here's the kaolinite. And here, I'll have you note, just look at this accumulation of kaolinite up through the saprolite to about 3 meters, and then there's something else that's going on here, and that's in the soil system, and we'll turn to it as in a moment. So that's really interesting. There's two kaolinite systems in operation here, the saprolite and the soil. So we'll get to that in a moment. Here's some work that my student, graduate Zach Breckheisen has taken the lead on, biological forcings of weathering. Here, the whole team, all of us at the Calhoun help Zach drill cores, some to 8.5 meters. We got nearly, let's see, I think we have 15 sites like this that go to 5 or 8.5 meters. And every 3 weeks, we monitor CO2 and oxygen. That's what's on the left, CO2, and on the right. Here's several years of data. And here's the biological signal, the greening of the summer and the dormant season, the wet season. You can see these characteristics in the CO2 cycle. You can see them in the oxygen cycle, the consumption of oxygen by respiration, the rediffusion in the wintertime of oxygen into the profile. And here I'll let you have something for Sue Brantley. We caught a very unusual event here. Here toward the end of 2015, the beginning, in the dormant season of 2015-16, we got 80, almost 85 centimeters of water, rain in 3 months in the dormant season, and that just really pushed the system hard. You can see over on the left that what that did was it dissolved a lot of that CO2, and it transported the CO2 out of the soil saprolite system. But boy, it wasn't cleansed. You know, there's a lot of microsites were bypassed that held on to their CO2. I mean, but it did overall over this 4-year period. It reduced those 2 or 3 tropical storms, 1 hurricane, really dissolved a lot of CO2 and transported it down into the saprolite, into those fractures below. And look what it did. It set up the next season to go from 3% to 7% in just a few months. And so I like to think of this as the wave of weathering. It's a seasonal wave of weathering. And here we got a real extreme case of respiration just accumulating 7% CO2. You look in Stum and Morgan, and we're working on the basic chemistry of the pKs of CO2, and we want to write basically an environmental chemistry about a basic chemistry paper on the reinterpretation of the pKs of this, what we see as a very potent weathering acid. And so it's basically lowered and concomitantly it's lowered the oxygen down to 8%. Here in the summertime, as respiration cranks up and diffusion in from the above ground, 20% in the atmosphere, above ground atmosphere, can't get into that hydrated, low diffusivity soil profile. So just to wrap up here, in number 1 of the 2, we have the critical zone as a clay mineral factory, a clay mineral. Kaolinite is a formation product. Now I'd like to turn to the second of the 2 parts, and in only a couple minutes deal with our hypothesis that we're still banging away at, and that is soil as a clay particle factory, a clay size factory, 2 micrometers or less. The hypothesis is that there's significant mechanical biomechanical comminution effects on the particles that are coming up the conveyor in the top 3 meters of soil, and the forces are by the growth pressures of tree roots. And here's a soil pit we've done with bulk density mapped, and in a 0.5 meter radial distance in the BT horizon, the clay-rich BT horizon, we have observed bulk densities over 2.0 grams per cubic centimeter. Amazing, just incredible. And so this is the basis of our hypothesis. And of course, above ground, we know that growth pressure is relieved by bulldozing, snow plowing the particles upward. And so here's the local proximity of the local elevation in proximity to a tree and of different sized trees. And so here particles being pushed away from the tree, 1 meter away from the radial distance. Down in the subsoil, the pressure can't be relieved, and so soil is compressed. So more recently, we're very interested in particle fracturing. So just look at this data here. Here's the clay size. So here are the particle size fractions. Less than 2 microns is 5% or less until 3 meters. And then bang, here's the clay BT horizon. The clay rich horizon is in the top 2 meters of the profile. All of that saprolite has a relatively constant particle size fraction, some variation, but until those particles are conveyed into the B horizon, perhaps in the soil creep horizon, that's when the BT accumulates. So that's our soil as a clay factory. And here's what we've done so far. I'll run this pretty quickly, but 2 processes we think are now hypothetically behind this clay accumulation. So here we fractionated the different particles down to 18 meters, and we were really amazed by this particle size analyzer showing that fine sands are diminishing as we go from saprolite into soil, B horizon, and the silts are accumulating through that time, and the clay really, of course, increases in this upper 1.5 to 2 meters. But the fact that we're decreasing the fractions of fine sands and in fact coarse silt is quite striking. We've had Paul Schroeder, so that was data from out of Alan Bacon's lab, who's studying particles ever more carefully. So here we took those same samples that in our lab, we fractionated the samples, sent them to Paul Schroeder, who's done some quantitative XRD, and this is really quite amazing. So here we have the top part of the saprolite at 3.5 meters. Here's the quantitative estimates of the minerals through his modeling and observations of QXRD. So it's got a little bit of kaolinite. Here it is. So the kaolinites are in the fine sand particles, and as those particles are conveyed into the B horizon, hypothetically, comminution is a process here, probably some kind of combination of chemical, physical comminution. But in any event, it's the case with the micas, the biotites, muscovites, and the illites disappearing. The red, there you go. It's the case even with the orthoclase, the feldspars, they're diminishing as well as you come into the B horizon. And then what accumulates are these kaolinites, and also some weathered muscovites, and some HIV, some hydroxy vermiculite, and some vermiculite. But in any event, this is a new process. It's not it's hypothetically a new process in the pedogenic literature. Most of this clay accumulation in nearly every paper is due to the eluviation of fine clays that somehow are mixed into the surface, but then they hydrologically are transported back because they're so small into the BT horizon, and they accumulate over time. I gotta move here, we're almost done. But I've taken the Piedmont soils, the official Piedmont soils, all the mapping units across that 30 million acres, across many different lithologies, and I've looked at the texture classes, no matter what the lithology, granitic to basic, etc. And we're looking at all of the residual profiles there, and almost all of them have saprolite that are quite coarse. They're sandy loams, or if they lack sand grains, they're silt loams in the saprolite. But then look at this, 80% of the soils on top are fine textured clays. And not only that, I mean, the clay is really extremely high, over 50% in nearly all of them in terms of mass of particles. And then in the A horizon, they become coarse again. So the literature has us characterizing these soil geomorphologic units as coarse over fine profiles. Coarse over fine profiles. The Calhoun Critical Zone Observatory is now redefining them, these same profiles, these same critical zones, as coarse over fine over coarse. And the point of the matter is we're testing the hypothesis of rhizogenic soil comminution in addition to the eluviation traditional way of looking at it. Yeah, amazing. And so we're back to here, soil as a clay factory, clay size particle factory, and that's what we've done here in this talk and in our work, that we share our data as Clarence Dutton says, we should share our data as a common stock. Amazing. Critical zone science links with 19th century science. We should share our data as if it's the common stock. And so I've told you the story of the soil and the critical zone from the bottom up. And last but not least, one more slide. And we are led in our critical zone observatory by a non-funded colleague, Terry Ferguson, who teaches at Wolford College. He has been our finest colleague over the many years, and he has led us into realizing and questioning the residual nature of the profile. And here I am in one of Terry's several dozen sites out across the Piedmont where he can say, this is colluvium, and here's an example, 6 meters of colluvium, and it's, in this case, it's on top of wetland organics. And so here I am, we're smiling, I'll tell you, we're grinning, because every soil scientist I know that knows anything about the Piedmont would never have predicted that there's any peat under the Piedmont. It's all residual. And so Terry, I'm tipping my hat to you. That story will be out. The first paper that discusses a little bit of this is our paper that came out in 2020. But Terry's leading the charge on a paper we hope to lead right into Science Magazine. So good luck, Terry. That's it for today, Sarah.
Thanks, Dan. Great talk. We lost a couple of people at the top of the hour there, but if anyone has a question, please feel free to raise your hand. I'll unmute you or use the chat box.
I'm going to ask a quick question. Dan, do you have any radiocarbon dates from those peats?
Carbon dead, every one of them. We now have some OSL dates from this colluvium. And we had a lot of beers on the lines, Tim. And I took an old age, and I won't tell you my bet, but I was betting against Terry Ferguson and Missy Epps, who some of you probably know, and they took the short. I don't remember exactly their age, but I'll tell you the OSLs. The one here in the colluvium up on top is paleo colluvium at 1 meter, 50,000 years. At 2, 3, and 4 meters, about 100,000 years. And that just blows my mind. I mean, just to think, and we've got like many dozens of these sites that are out there. So great question, but it's carbon dead. And we've done pollen work through these profiles, and some additional OSL dates are coming. Some of these organics have plant fossils, insects, leaves, acorns. In any event, yeah, we're back to Heraclitus here. I mean, this is a lot of flux. Amazing. Thank you for your question.
Given those dates, it sounds like it could be last interglacial.
You bet, absolutely. And to think it was only the last glacial cycle. But what about all those other ones before that? I mean, and here we have a Piedmont that's still in the textbooks as, you know, as kind of an outlier, where soil scientists have appreciated that more and more of the earth formed soil in particles that have been elsewhere, that have resided elsewhere, and not just in floodplains or by glaciers or by loess or whatever. But that's really the generalization you can make, is that most critical zones have soils on top that are formed of transported materials. Yeah, so look for Terry Ferguson's paper on we've taken apart one gully, and I'll wait for any other questions, but I'll tell you this little anecdote. The gully that we've really spent a lot of time with is right near the Calhoun Critical Zone Observatory. It's got an organic layer, and this is the carbon data from it, and it's got the OSL dates that I just mentioned. But in the bottom of it is a whole house. It's a rural southern landscape. And who pushed the house into the gully? But the Marshall Tucker Band. The Marshall Tucker Band was living on this particular land, where we've investigated the gully. And at the end of the day, they pushed their house into the gully. Oh my God. The Piedmont is an excited place.
Dan, nothing against your science, but that's the best part of the story.
I agree.
That's great.
On that note, I don't think we have any more questions, but thanks, Dan. That was a great talk.
Yeah.
Thank you, Dan.
Thank you all.
See ya.
Thanks, everyone, for attending.
Thank you, Tim and Sarah.
No problem.